Welcome back. As part of this session, we'll talk about data structure trees. Okay. So, trees are hierarchical data structure that consists of nodes connected by edges. Example, these are the nodes and connected by edges. This is what tree is. It's very simple and they are widely used in computer science and have various applications such as representing hierarchical relationships, organizing data efficiently, and implementing algorithms like search, sorting, indexing, this kind of operations on that. A tree is a composite of nodes with each node will have zero or more child nodes, right? That the topmost node is called a root node, and the each node in the tree has the parent node, right? And the nodes which doesn't have any nodes are called any child nodes are called leaf nodes, and the nodes are of the same level are called siblings. So this is very simple to understand from the left side graph, left side tree. Trees can be classified into different types based on the properties, such as binary tree. What is binary tree? A binary tree is a tree where each node has at most two childs. Commonly, we will represent as a left child or right child. There is a binary search tree. A binary search tree is a binary tree that satisfies the one property. The property is all the left subtree has the value less than the its value, and all the nodes from the right side will have greater value. So this property will give some kind of efficiency in searching, insertion, deletion operations. Basically, it is big O of log n in average case. So making BSC suitable for the application that require fast retrieval of data in a sorted order. Balanced tree. A balanced tree is a tree where the height of every node's left and right subtrees differ by the most specific balance factor. Basically, AVL trees, red black trees, B trees, right? These are balanced trees which maintain operations ensuring that relatively balanced and preventing the degradation of time complexity for worst case scenarios to retrieve, insert all operation. We'll see those things in next coming slides. Tree traversals. Travels refers to visiting each node in a tree in a specific order. There are two common methods we can use. One is the depth first travels, and second one is breadth first traversal. So, using depth first traversal, there is in-order traversals, the pre-order traversals, and post-order traversals. In-order travels basically you can visit left node and the current node and the right node, or basically like a subtrees. Pre-order means visit the current node, then traverse the left subtree and then right subtree. Post-order means first traverse the left subtree and right subtree and then the current node. Coming to breadth first threads, this basically like a level by level traversal, visiting nodes at each level from left to right. Tree search algorithms. This also algorithms also like a depth first search as we discussed in here, like in order, post order like this. So basically, this traversing will start from the root and explore as far as possible along each branch before backtracking. And BFS explore all the neighboring nodes at the current level before moving to the next level. This can be implemented using queue data structure. And space complexity related, the time and the space complexity for these operations depend on the type of the tree and the specific operation being performed. Here are some common time complexities. Binary search tree, average case, equal searching log n, insertion also of log n, deletion also of log n. And worst case thing, unbalanced BST, it will take often because we need to worst case actually I'm saying. And we'll discuss more about these things in the coming sessions. So in the balance rate, all like a bit of log n only. Coming to T traversal, like in order, pre-order, post-order, it will be taking off and visiting each node at once. And the tree search algorithms again, BFS. Actually, it will take big O of number of vertices plus edges. Similarly, BFS also, it will take big O of number of vertices plus edges. The space complexity of tree operation depend on the recursive nature of traversal and algorithms. In general, for balanced trees, right, the space complexity will be O of log n. Okay, yeah. For unbalanced trees, yes, the complexity will become O of n because of the worst case, it will screw the data structures. That's it about this session.